Today is going to be 83-1 and we're going to take a look at other algebraic functions. Today we're going to be able to manipulate and simplify exponents and radicals. Now, rewinding back to intermediate algebra, we learned about root expressions. Now it said that let x be a real number and n be a natural number. If n is odd, the principal nth root of x denoted, so this being an odd number, so an odd root of x, is the unique real number, satisfying it. What this is referencing is the fact that there's no ambiguity. So the cube root of 8 is 2. The cube root of -8 is -2. There is an actual unique number that satisfies it. Now when n is even, the even root of x is defined similarly to be provided for we have to have a value greater than or equal to 0 so that this entire statement has to be greater than or equal to 0. Now the reason why we say that is because remember, even with the basic value x squared, let's say if I have the square root of -4, what value squared gives me -4? And there are none. And that is the reason why, because of that ambiguity, we have the domain restriction where we have to say whatever's inside there has to be greater than or equal to 0. So this is telling us that roots and powers cancel out when they are the same, and also if the root is even, so the n is even, then the value of our domain has to be greater than or equal to 0. So things do cancel out, and they do cancel out, so that's why the square root of n to the n power, those are going to cancel out. And then if your root is even, it has to be greater than or equal to 0. Now just kind of like punching them into a calculator, if I wanted to imagine the square root of x, the fourth root of x, the sixth root of x, for each even root that we're taking, it just looks like this value right here, it seems to increase, and this gets a little flatter, but it's still a one-to-one function. Likewise, if I say cube root, fifth root, seventh root, right, it looks like this part's getting a little straighter. It's not, it just looks a little straighter, and this ends are getting a little flatter. And so that's just something to kind of keep in mind, just kind of visualizing what it's asking us. Now we're going to go over a few properties. So a few properties of radical. If I say that the nth root of x and the nth root of y are real numbers, then the product rule, the nth root of xy equals the nth root of x times the nth root of y. Power of radicals, all this is saying is that if I have a power on the inside, I could bring it to the outside. The quotient rule says that if you have the nth root of things divided top and bottom, you can rewrite it as the nth root of the top over the nth root of the bottom. But this is a two-way statement, so like you could also, if you had it like this, you could end up writing it like that. And then if n is odd, then you know it's going to be x, but if n is even, it has to be the absolute value of x. And the reason why we say that is it has to be positive inside there. You can't have a negative value inside of there. And so we have to make the assumption that our x has to be positive. So let's do a few of these. So this one here, I could say the cube root, I can say this is x to the third to the fifth power, because I know that x to the third to the fifth is the same as x to the 15th. And so those would cancel out, and so you're just going to get x to the fifth. For this one here, this next one, we're multiplying, so this is going to be the fourth root of x to the fifth. And so the way that we can actually simplify this now is, I want to kind of break this up. I could break this into the fourth root of x to the fourth times the fourth root of x. And so now this would cancel out, so I'm left with x, and then I'm left with the fourth root of x. For this one here, remember we can break them apart, so I can say that this is the cube root of x to the 9th over the cube root of y to the 12th. And so we can break these apart. I can say that this is the cube root of x to the third power, the cube root of y to the fourth to the third power. Sorry, y to the third to the fourth power. And so the cube roots cancel out, the cube roots cancel out, so you're left with x to the third over y to the fourth. Now you probably have already adopted a pattern. Well, hey, what if I divide the 3 into the 9? I get 3. If I divide the 3 into the 12, you get 4. If I divided the 4 into the 5, you get 1, and you're left with 1 left over inside. So there's that pattern that does exist. And for this one here, this one is a little different, and because this root is different than this root, we actually can't combine them together because our properties, they say they always have to be the same. But now that is an issue. This is an issue because we can't combine it together in its current form. But what if I transform this into an exponential function? And so if I let x be a real number and m an integer and n a natural number, then I could say that x to the 1 over n is the same as the nth root of x. The x to the m over n is the same as the nth root of x to the m power, or the nth root of x to the m power. Now, one thing that you just need to remember, whatever your exponent is, or whatever the exponent is, whatever you're dividing by, that's the root. Whatever your power is, okay, whatever's on top or on the numerator, that's your that becomes the actual power when you're trying to convert it into a root. So in this instance here, this is x to the first, so I can transform this into x to the 1/3 times x to the 1/4, because that's a root, it goes in the denominator, that's a root, that goes in the denominator. Now this is in terms of powers here, I can combine those together because they have the same base. Now remember, when they have the same base, you add the powers. So I'm going to add the powers together. 1/3 plus 1/4. Top and bottom is 4. Top and bottom is 3. So you get 4 over 12 plus 3 over 12, which equals 7 over 12. And so this is going to be x to the 7/12. And that's going to be your answer. And so we're actually, by converting, it makes it much easier for us to be able to even simplify these. So in this instance, if I were to convert this, this would be, this is the root, so that's in the denominator, that's the exponent, so that's going to be on top in the numerator, so this should be x to the 4/3. This one would be x to the 25ths, which reduces into x to the 4th. Now this one here, we have a series of these, and so this would be x to the 2/3 times x to the 4/6 times x to the 7/3. Well, I can combine those together, so I need to find the common denominator. Remember, if their bases are the same, you add the powers. So 2/3 plus 4/6 plus 7/3. Well, this needs a 2 over 2. This needs a 2 over 2. So you get 4/6 plus 4/6 plus 14/6. And that's going to give us 20. That's going to give us 26. And I could reduce that into 10/3. And so I can say that this is x to the 10/3. Now, part of the reason why we can do that is we can actually simplify these expressions here as well. Because now this becomes x plus 1 to the 2/3 times x plus 1 to the 3 over 1. Sorry, 3 over 2. Because remember, if it's a square root, then there's like that imaginary 2 there. So now they have the same base, so adding the powers together, so 2/3 plus 3/2, this needs a 3 over 3, this needs a 2 over 2, you find the common denominator. So you get 4/6 plus 9/6, and that'll give me 13/6. So I can say that this is x plus 1 to the 13/6 power. So what concepts were discussed today? We examined being able to convert back and forth between exponential functions and root functions. Why would it be important to convert into an exponential notation? And also, how do I find the composition of functions again? I kind of forgot. It's been a while. So if you guys want to go ahead and post those in the comments, I want to see what your guys' responses are. And if you have any other questions about this lesson, please leave them in the comments.